Hi, today my name is Paul Horn. I'm a statistician in the neurology division at Cincinnati Children's Hospital. And today I'm going to talk about statistics and specifically analysis-of-variance, henceforth ANOVA, and regression analyses. But first we will talk about the design of experiments and give some simple examples. Let's start out with a simple example to show good design of experiments. Suppose we wish to compare two anti-epileptic drugs, D1 and D2. We have 60 patients, say, 30 males and 30 females. And we assign drug 1, D1, to the males and drug 2 to the females. And the response will be the seizure frequency at 6 months of follow-up. So the problem is that any difference between these AEDs is confounded with gender. And of course, I hope none of you would run an experiment this way, of course. And it's clear that a better way to run such an experiment would be to stratify by gender. And basically that just means let's randomly assign 15 males to drug 1 and 15 males to drug 2. Do the same for females, and now the experiment is balanced. We say it's balanced with respect to gender. And so now any possible gender differences can be examined for each drug and then pooled. Okay, so in this example, the seizure frequency at 6 months is referred to as the dependent variable. In other words, if anything, this variable depends on the drug and perhaps gender. So AED, the drug, was the independent variable, and I put here of primary interest because that's usually the case, that the drug is of primary interest. Gender was a factor in this case, and it's referred to sometimes as a covariate. Specifically, it is also an independent variable, but we make that distinction between the variable of interest. You want to look at the two drugs, and gender is there. It's maybe of secondary interest, but it is called a covariate. In this case, it is also a blocking variable in the design of this experiment. And other potential covariates / blocking variables are going to be other demographics, of course. They could be race, age group, household income, etc. In a multi-center study, or even a big study within one area, hospital could be a blocking variable. And of course, attending physician or doctor could be another blocking variable. And just as you probably are aware, doctors often will work for just a single hospital, so we would say that they are nested within hospital. And that's really the subject for a more advanced talk, but it's something to keep in mind. And the point is we want to achieve balance as much as possible with respect to blocking variables that we consider important a priori. So in other words, if we suspect that gender may be important, and every study and every proposal I've read has gender and often race as an important factor, we would like to achieve balance if possible with respect to that. And one thing I want to note, because I see this a lot with the people I collaborate with, is just because we achieve balance with respect to a variable does not mean we should ignore it in any subsequent analyses. In other words, if I think gender is really important and I balance for it, which means it's not going to confound with the final treatment effect, doesn't mean I shouldn't account for it, though. It may explain a lot of variation and therefore make for a better study. Okay, so that brings us to analysis of variance. Again, henceforth ANOVA. I think this will be the second and last time I will actually spell that out. And basically we need to keep in mind statistical inference, and this will be a quick review because some of you have probably had a biostatistical course at some point or another AES short lecture. But basically, in a nutshell, we believe the data should behave in a certain way, and that is defined as a model. We then observe real data which do not necessarily adhere to this model. I mean, this is real world versus theoretical world. And the question is, are the deviations from our hypothesized model the results of spurious noise, or is the model wrong, or is our model correct and we just got a bad sample? And those are all questions that we try to tease out with statistics, and there's a very famous quote by the statistician, very famous George Box, who said that all models are wrong, but some are useful. Models are an approximation to how we believe the world, the real world, may behave. So the way I like to think about it, and this, you probably didn't expect to see this, a little bit of grade school geometry, but basically the real world or the observed data is going to basically do its thing. It's a vector or a line, the hypotenuse in this case, and we call observed data y with a little arrow over it, and that pertains to just basically that's the way things are. On the other hand, we have a model that says, you know, these data really should live on this line. That's the perfect situation. And then the question is, well, how can we get the data to appear on this line? We actually project it. We make a perpendicular bisector. Notice that's 90 degrees there. And we say, well, how far is it from this model? That's how far. And this would be y hat, which is the fitted data based on this model. And in statistics, we always put hats above things to show that we're estimating something. And of course, now from your elementary geometry from grade school, you know that the side opposite, or this leg of the triangle, is the residual. It is the observed, the hypotenuse, minus the fitted. And that makes a 90-degree angle. And so the fitted value is the model if it's true, and the observed, which is the hypotenuse, is the sum of these two vectors. Not the length of it, but that's how you get vector summation, if you remember way back when to your early math days. But what is true of right triangles, which everybody I hope will remember, is that the length of the hypotenuse, which in this case is the raw data, so the raw data squared is equal to the square of one leg plus the square of the other. And so you have the Pythagorean theorem that comes in that says the square of the observed is equal to the square of the fitted plus the square of the residual. And it's hopefully clear that this residual vector, if you will, but this line, if that's really big, so I'm just using two greater signs, if that's really big, then the model can't be very good, because it means that your observed data is really far away from your projected or what you believe reality should be. And the worst case would be, of course, you can imagine, if this line were perpendicular to this, then it's like it's all residual and your model is just awful. So this is, I like it as a picture. It helps me, and I'm not the most graphically oriented person in the world, but this is the picture to keep in mind, that real world, model, and this is what's left over. And that's that's analysis of variance in a simple picture. Okay, enough of that. So let's recall our two AEDs. The response is seizure frequency after 6 months of follow-up. And for now, we'll just consider the difference between the two means, y1 bar minus y2 bar. And I'm actually violating what I said before. For now, we're going to ignore gender, but we will bring it back. So let's assume that the truth, in other words, the true means for each AED reduction in seizure frequency would be mu1 and mu2. Now, mu1 and mu2 are Greek m, lowercase, and we usually use the Greek letter to represent the English letter m. So mean is m, Greek m is mu, so in a nice world, the mean of the first AED should approximate the mean of the hypothesized mean, and Y2 bar, the sample mean of the second AED, should approximate mu2. So, from hypothesis testing, again, this is a bit of a review. The null hypothesis, H0, is that and this is usually the null hypothesis, doesn't have to be, is that these two population means or theoretical means are in fact equal. The alternative is that there's a difference between these two drugs, okay, in mean value. And as you may recall, H0 is rejected in favor of the alternative hypothesis, H sub A, if this difference is too extreme. And I put extreme in quotes because we know they'll be different. It'd be very unusual to get two means that are exactly equal, okay? But how different is too different? Okay, so how extreme depends on the amount of error not explained by the difference. Now, I will just preface, this slide has a lot of stuff on it. Don't be intimidated by it. You may have seen, those of you that have had a biostat course, you may have seen things like this before, but the gist of it will be made clear, and it's pretty simple, actually. So if you recall from hypothesis testing, we had a t-statistic to measure the difference between two means. In the numerator, we have y1 bar minus y2 bar, the sample mean from the first drug minus the sample mean for the second drug, but we divided it by, and I'm just calling this residual error, times a factor that represents how large the sample sizes were for each of these two groups. So I had, say, N1 observations from group 1 and N2 from group 2, and that's just a factor to reflect the fact that these two means are based on sample sizes, hopefully greater than 1 would hope so. This slide can be summarized in this parenthetical remark. Basically, this is a signal-to-noise ratio. The signal, the numerator, is how different are these means that we observed? Y1 bar minus Y2 bar. That seems like a good signal to me. The noise is what's left over. And if your signal is strong enough to break through this noise, in other words, if this ratio is large enough, and large enough could be positive or negative because I didn't take absolute values here. Y2 bar could be a lot bigger than this guy. If that's large enough, then we would reject H0 in favor of HA at a level alpha, which you may recall. And that is if T is too small, in other words, if Y2 bar is too big, if it's less than this value, negative T sub alpha over 2 nu, or it's too big. Now, what is this fellow here that looks so complicated? He's not that complicated. It's basically the upper alpha over 2 percentile of a student's T distribution with nu degrees of freedom. That's Greek nu, and as I said before, what is nu? It's Greek n, and it's lowercase n, so it is the Greek equivalent, really, of n. And for the two-sample case, nu is often equal to n1 plus n2 minus 2. Okay, so there's a lot of math there, but the essence is this. We're looking at signal-to-noise ratios, and that's not going to change, really, for pretty much this whole lecture. So if you recall from hypothesis testing, the residual error is equal to what looks like, again, a complicated formula. It's really not. It is the square root of some combination of the sample variances. S1 squared and S2 squared are the sample variances from these two samples. You're probably more familiar with S1 and S2, or just plain old S, which are standard deviations. But if you square a standard deviation, you have a variance. And so what we're doing here is we're taking a combination of S1 and S2 squared. We're sort of averaging it and then taking the square root. And that's where you get this S sub P is a pooled estimate of residual error, or if you prefer, it's a pooled standard deviation. That's all it is. And in fact, if you take a quick look here, if N1 and N2 are actually equal, what happens? It turns out this is just the average of S1 squared and S2 squared. It's S1 squared plus S2 squared over 2. You take the average of the means, and then you take the square root. So SP is a pooled estimator. I just note here, because I'm a statistician, it's not always the case, but as far as we're concerned, it is. Okay, so again, a lot on this slide, but the two takeaways are you test using a signal-to-noise ratio, and we consider that the noise is pooled across samples. Case closed, easy peasy. Okay, now we get to the tough stuff, or the essence of the talk. What if there are more than K groups where K is greater than 2, or more than 2 groups? Well, 2 groups were easy because you had Y1 bar, the average of the first group, minus Y2 bar, the average of the second group. What do you do if you've got more than 2 groups? Well, now we look at a model, and we'll look at K groups. So we'll model the jth response from the ith group. In other words, the jth person, say, from the ith treatment group. So that will be Yij. The response, the model, is equal to some alpha, which is an overall level called the grand mean. Something like if you're measuring systolic blood pressure, well, you may be looking at different blood pressure treatments, but everyone's going to have some, constant that gets added, and then we're going to look at the differences. Tau sub I will be the effect of being in the ith group. And notice we use tau. What is tau? Tau is Greek letter T, and it's really standing for treatment effect. So the effect of being in the ith group or ith treatment group, this is a biostat mostly. N sub I, again, is the number of observations in the ith group. Often they're equal if we can help it. We usually like them to be equal, but they don't have to be. Epsilon ij is basically what makes the model go statistically. It adds some randomness to it. It says, in a perfect world, Yij will equal to alpha plus tau I, but that's never going to happen. So we have to model noise, and epsilon ij is a random error modeled as a normal distribution with a mean of 0. In other words, there's no systematic bias. That seems reasonable. And variance sigma squared. The normal distribution, as you know, is the bell curve, the traditional bell curve. And so it is often the case that the null hypothesis here is that the means are all equal. Tau 1 and tau 2 up through tau sub k are all the same. In other words, there is no difference among these treatments, so that these responses would all be the same. But now the question is, how do we test this? Okay, so we want to test whether or not there are differences among several means greater than 2. We already know how to do 2 from the 2 sample test. So recall, we have a null hypothesis that all the treatment effects are the same, there's no difference, and the alternative is that there's at least one pair which are different. In other words, you could have 20 treatments, 19 of them could be exactly the same, and one of them could be the oddball, and that will be part of this alternative hypothesis. There are other alternatives one can come up with, but they're beyond the scope of this lecture. So the 2-sample T statistic doesn't look promising. It can only look at 2 samples at a time, hence 2 sample. So as I said before, this is a signal-to-noise ratio. So the numerator measures the difference between 2 means. And here's the insight. If the null hypothesis is true, then you would expect all K sample means, which now we'll just call Y1 bar, meaning the sample mean, the sample mean from the first group, Y2 bars, the sample mean from the second treatment group, all the way up to the Kth sample group. So we're going to take all those K averages. If there's no treatment effect, these should be not equal to each other, but they should be similar, approximately equal. And so now we need an appropriate signal-to-noise ratio. We need a numerator that measures the differences not between 2 things, but among K sample means. Okay. And the denominator, again, could be some residual noise. That's how we decide, is that difference, is that numerator, is that signal significantly greater or greater enough over the denominator of residual noise to make us say, aha, this cannot be true. So, if the null hypothesis is true, you would expect all sample means to be similar. If they're all similar to each other, then they will be similar to the overall grand mean. In other words, the mean of all observations. Think about that for a second. It makes perfect sense. If I have k treatment groups and I take the mean of each group, but there was no difference to begin with, well, then I could have just taken the mean of everybody and ignored treatment. Sounds reasonable, I think. And so now we can consider y bar without a subscript as the mean of everybody. And so now we'll look at the squared difference of the first sample minus this grand mean, the second sample minus the grand mean squared, and the kth sample minus the grand mean squared. And this is called, this has a name, that's why I'm talking about it. It's the sum of squares due to the treatments, and it is abbreviated as SST. And we can actually now look at a mean with respect to these fellows. We define the mean square due to treatments as the sum of squares due to treatments divided by, well, how many treatments did we have? K. Its degrees of freedom is k minus 1. And we call that MST for the mean square due to treatments. And here's the important point. This is basically like treating group means as single observations and computing the variability versus a grand mean. So it's really in the spirit of a variance. And it's similar to two samples now. Let's look at the residual noise. Each of these samples, and I know this slide is a lot, and it's about as complicated as it gets, but basically if you break it down, it's not too bad. This is the variance, S1 squared, from the first sample. This is the variance from the second sample. Now, I hope you were comfortable with the two-sample case where we did this. Whatever you can do for 2, you can do for k. So now we'll go all the way up to the kth sample variance, and it gets multiplied by nk minus 1. And then we just divide by the n1 minus 1 plus n2 minus 1 plus nk minus 1. That's the same as adding up all of those, which is the total sample size minus k, 1 for each treatment. This guy here, the square root of this pooled variance, is called the root mean square error, RMSE. And in fact, in the two-sample problem, which you remember from your either a previous slide here or your biostat course, that's also a root mean square error. It just happened to have k equal to 2. And we call the numerator here has a special name. It's called the sum of squares due to error because it's the sum of squares. Seems like a reasonable thing to talk about. So it's the sample variance times the sample size minus 1. And if you look at the math, it is just adding up squared deviations, and we add them up through the k groups, we get something called the SSE, or sum of squares due to error. Anytime you have a sum of squares, you can have a mean square just by dividing by its degrees of freedom. And in this case, it's n1 plus n2 all the way down to n plus k minus k. And this is the mean square error. Okay, admittedly, a lot of math, a lot of symbols, but that's what computers are for. It'll do it all for us. It's the concept that is meaningful. Okay, so what's the main concept? The concept is that the mean square due to treatments divided by the mean square error is a ratio. Now, what have we been concentrating on in this lecture is that ratios are signal-to-noise ratios, and that's exactly what this is. It's called F, the mean square due to treatments divided by the mean square errors. It's distributed like something called an F distribution. And the F stands for Fisher. Ronald Fisher, considered the father of modern statistical analysis, who happened to be a geneticist about 100 some odd years ago, and Fisher has a lot of things named after him. So this ratio, if we think of it as a signal-to-noise ratio, what do we do with signal-to-noise ratios? If the signal is really large relative to the noise, we declare that there's something going on and the null hypothesis is not true. Now, just as a sidebar, the F distribution has two parameters. It has a degrees of freedom for the numerator. In this case, it's k minus 1. And the degrees of freedom for the denominator is n minus k. And here, n is all of the observations. I don't think I had that in the slide, but it's n1 plus n2 plus all the observations, all the way up through nk. And k is the number of treatments. And being, as I said, any signal-to-noise ratio, we reject H0 for large values of f. An example, is there any difference among the 3 AEDs? We'll measure seizure reduction after 8 weeks. We have 4 subjects for each AED with these results. And as you can see, there's a lot of numbers to compute. We're not going to do that. There are means, standard deviations, there's variances, there's all sorts of things. Clearly, though, just eyeballing these data, you don't always get this luxury, but you can see D2 looks best, where more is better in this example. But is there enough evidence to claim that the differences are statistically significant? So let's organize the information for the purposes of addressing this issue as to whether or not to reject the null hypothesis. Okay, the ANOVA table, we summarize all the data in this very slick way. We have something called the source, which in this case is treatment. That'll be SST. It has k minus 1 degrees of freedom. It has a mean square, and it has a ratio, an F ratio, which will utilize the second source, which is error, sum of squares due to error, degrees of freedom, mean square error. We've covered all of this already, and we just take this ratio, MST over MSE, and we can get a p-value. Notice that the sums of squares add up. That's our friend Pythagoras again. I wouldn't be surprised if that's one of the only times that Pythagoras has been quoted in one of these lectures. And so from this example, we just plug away. We let the computer do its job. We get a sum of squares. These should add up. The degrees of freedom add up. The mean squares do not add up, but they're useful. And so we get an F ratio of 11.73 and a resulting p-value of 0.0031. This p-value is statistically significant. It is smaller than 0.05. And that is the typical value that we use for alpha level of significance. We don't have to, but it's traditional. So we reject the null hypothesis and declare that there's a difference in mean response among these 3 AEDs. Notice we don't know what's really going on yet. We just say that there is a difference. And notice that the root mean square error, which is not in the ANOVA table, but it usually appears somewhere else, is the square root of the mean square error. In this case, it's 3.57. And the degrees of freedom associated with this fellow is 9. So one way to think about it is that each drug, each of the 3 groups, which had 4 observations, each is contributing 3 degrees of freedom to estimate error. Okay, well, we have a significant result. Now we can go to post-hoc comparisons. So we can now look at specific differences. And here we can look at pairwise comparisons between pairs of AEDs. And now we can just look at our friend, the 2-sample t-test. So this is now old news. The only difference is we're going to use the pooled standard deviation of the ANOVA, not the pooled standard deviation from 2 samples. So we're going to use the root mean square error from the ANOVA, and so we're going to have 9 degrees of freedom associated with that. So let's look at Y1 minus Y2, or AED D1 minus D2. Here's the sample mean from the first group minus the sample mean of the second. We get a difference here. Our t-statistic, notice what we use for our residual noise is the root mean square error. We get a t-value of minus 3.87. We compare this to a student's T with 9 degrees of freedom, because this is now a pooled ANOVA, yields a two-sided p-value of 0.038. Similarly, Y1 and Y3 have a T statistic equal to 0.59 and a p-value which is pretty large. And again, when we eyeballed those data, those two groups did not seem that different. Y2 minus Y3 is another large difference. T is very large at 4.46 and its p-value is 0.016. So as we suspected by eyeballing the data, AED2 is statistically significant from the other two AEDs, but why AED1 and AED3 do not appear to give different answers or different statistically significant results. So what if there are multiple factors like gender, age group, etc.? Okay, so now we're going to go back to the previous example where we had 3 AEDs and we had 4 observations, but suppose now we actually knew what the gender was as they were spread out among these 3 groups. And suppose the AE data had this structure. Since we originally balanced for gender, we thought it might be important. So it should appear in now what is called a two-way ANOVA. Before we had a one-way ANOVA, meaning there was only one factor we cared about, which was treatment. Now we're going to bring in treatment and gender. And so now we'll model YIJK. Notice there's a third subscript as alpha, some overall level, plus the effect of being in the ith treatment group. So either AED 1, 2, or 3. So I goes from 1 to 3. There were 2 genders, beta 1 or 2, and 2 observations for each gender drug combination. So we'll just say beta 1 is the effect of being female, beta 2 is the effect of being male, and epsilon IJK is the error associated with the kth observation in the ith group and the jth block, gender. Notice I'm calling gender a block. Starts with the letter B and thus gets lowercase Greek beta as a letter. Okay, so does gender make a difference? Will it help taking gender into account? Well, now you recall we had our old friend, the ANOVA table, summarizes all the data quite nicely. Now, instead of calling this first sum of squares model treatment, we'll call it the model sum of squares. And it has 298.83. It has 3 degrees of freedom. Error has 8. It must add up to 11, which is n minus 1. Big N was 12. There's its means, the respective mean squares and the ratio, and we still have a significant effect. So here, one thing to note in this model, is that the model term contains the treatment effect as well as the block effect. It contains everything. So, and it has 3 degrees of freedom. 2 degrees of freedom come from the 3 treatment groups. 1 degree of freedom comes from the 2 genders. And hence there are 3 degrees of freedom total for the model. That means there must be 8 left over for error. It turns out that the effect of these 2 effects, the treatment effect and the block effect or gender effect, can be separated. And in fact, that's how most software packages will separate things out. It will give you the overall treatment sum of squares and the block sum of squares. And there's just simple algebra and math that lets us do this. And notice the degrees of freedom are broken out respectively into 2 and 1. And remember what I said, we can have a mean square. So here the mean square will be this sum of squares divided by 2. This is only 1 degree of freedom, so the mean square happens to equal the sum of squares. And error has its mean square. And anytime you have a mean square with a mean square error, you have an F ratio. So here, that's our overall model p-value, which we already knew. But it can be broken down to a p-value that's due to treatment, which is highly significant, and gender, which happens not to be. So notice that is a very big p-value. It is not significant. So based on these data, the block effect or gender is not important. And one thing that's kind of interesting is that by testing for gender, what happened? The mean square error actually increased a little bit. In the previous case where gender, we didn't know about gender or ignored it, the mean square error was only 12.72. Here it's 14.27. So you do lose a little by testing for factors that are unimportant. But as a highlight here, we didn't know that. I mean, you don't test things you know, but we didn't know that. But it turns out if it were significant, and which will happen sometimes, it would probably have reduced the mean square error, and you'd have gotten more precise. And think about how important that is, and we'll get to that in a second. Okay, so multi-way ANOVAs have the same format as two-way ANOVAs. So once you've broken through with two, just like two samples gave way to multi-samples, multi-way ANOVAs have the same format as a two-way ANOVA. There's an overall model p-value. The model sum of squares can be partitioned into sums of squares for each effect. I mean, you can imagine in the previous study, I mean, you could have a whole lot more observations than the 12 we had. You could have treatment, you could have gender, you could have race, you could have age group. And all of those could go into a model, and each effect has a degrees of freedom associated with it, and thus a mean square. And the degrees of freedom can also be partitioned. Like again, mean squares cannot be partitioned, but the degrees of freedom can. And an F ratio is formed by dividing the effect's mean square by the mean square error. Now, there are more complicated models where there will be different denominators, but that's beyond the scope of this lecture today. Since the mean square error represents noise, we'd like it to be small relative to the signal. I mean, we want to account for as much that we can explain as we can. And so the term we use is we like to have parsimonious models so that we can have lots of degrees of freedom for error. As you saw in the last slide in the previous example, that by testing for an effect which wasn't important, our mean square error actually increased, which means our noise increased, which means our denominator increased, which meant that our sensitivity or our power to detect the difference took a little bit of a hit. Okay, so we do like parsimonious models, but if we think something's important a priori, like gender, we must put it in the model. Okay, that brings us to one of the other major topics of this discussion today is correlation. Well, most people know what correlation is, but we'll just go through it rather a little quickly. Correlation measures the strength of a linear association between two continuous type variables. Think of height and weight. The sample correlation coefficient R lies between -1 and 1, so that's mathematically what we say. If it's less than 0, we say the variables are negatively correlated. If it's greater than 0, they're positively correlated. If the sample correlation coefficient is equal to plus or minus 1, then you have a perfect linear relationship. Your points would lie on a straight line. And if R is 0, then there is no linear relationship between the two variables. And one thing to note is the sample correlation R is an estimate of the true unknown, what we call population correlation. And guess what letter it gets? Rho, which is Greek R. So Greek R is what we would love to know, but we'll never know it. You would have to examine everybody in the population, but we have a sample correlation coefficient. So hopefully it'll be a good estimate. Okay, so here's an example of positive correlation. These points don't lie exactly on a straight line, but they're pretty darn well correlated. These points are correlated also pretty well, but they're in a negative direction. Negative meaning that as you go to the right on the x-axis, you're going down on the y-axis. That's negative correlation, or negative slope. And here the correlation, these points are going all over the place. It's just basically a cloud of noise. So if you fit a straight line through these data, the sign of the slope would be the same sign as that of the correlation. This would be a positive slope, that's negative, and this would be approximately 0. And let's look at an example that I looked at here in neurology, and it's the relationship between radionuclide injection latency and seizure duration for SysCom. Means more to you people than it does me, but the important thing is we will look at two variables. We will look at seizure duration versus time to inject, or injection latency. And in statistics, it is always y versus x. So seizure duration will be the response on the y-axis. The time to inject, or injection latency, will be on the x-axis. So let's look at some data. These I would love to say these are real data, but because of, patient data and everything, I simulated these. So these are made up data, but the spirit is the same. So these are points where this is seizure duration on the y-axis and injection latency on the x. The correlation coefficient is 0.65. They're positively correlated as expected. Hypothesis test is typically it's rho equals 0. In other words, you say there's no correlation versus the alternative is that there is correlation. In other words, it is non-zero. Turns out the p-value for this test is 0.002. So the conclusion is that these variables are significantly correlated. Okay, the next major topic here is linear regression analysis. Recall that correlation measured the strength of a linear relation. In other words, there is a slope and an intercept. A positive correlation is indicative of a positive slope, and a negative correlation indicates a negative slope. Uncorrelated data have slope approximately 0. In other words, a horizontal line is the approximate fit. In regression, we estimate the fitted line itself. So these are two, they go hand in hand, regression and correlation. If there were no errors and y is a linear function of x, then we would expect that y would equal beta naught plus beta 1x, where beta naught is the true intercept and beta 1 is the true slope. And so, since we can never know these for sure, if we knew them, then we wouldn't bother estimating them. We have a model that says that y is equal to beta 0 plus beta 1x plus epsilon, where epsilon represents random error. As in analysis of variance, epsilon is assumed to have a normal distribution with a mean of 0 and unknown standard deviation sigma. How do we estimate beta naught and beta 1? And this is standard notation in statistics. When we get to parameters like this, it is beta that is used for all of them, the slopes as well as the intercepts. But our estimates are going to be things that we actually compute. So suppose B0 and B1 are estimates of beta naught and beta 1 respectively. Then for a given data point, this is an observation, we have a fitted value of y. Remember way back when to our early slides where we say estimates get hats on them. So the estimated y will be yi hat, and that will equal beta naught plus beta 1 xi. Now that's a true equal, but that's an estimate. We didn't observe that. The residual is defined as the observed minus the fitted, or the modeled. Recall that from one of our slides. And so the residual, R, not to be confused with correlation, it's just the letter R for residual, gets Ri hat is equal to the observed y minus what we think it should be. And we would like to find a line that makes these residuals as small as possible. And that leads us to the least squares criterion. We want to find a beta naught and a beta 1, a slope and an intercept, to minimize the sum of all squared residuals, the sum of all of the squared residuals. And so we want to take the sum of all these residuals squared, and we can find a B0 and a B1 that minimizes this among all possible candidates. And this is actually quite a simple problem in calculus. And of course, we're not going to go through that, but it can be done. And this is called ordinary least squares, and it is the most commonly used approach in linear regression. So the problem It looks complicated, but it's really not. So now when we go back to our syscom data, I fit a least squares line through this. And what makes this the least squares line is that if we look at these, what are the residuals? The residuals are these vertical distances. This is the observed, and this is the modeled for that particular x value down here. So if you look at the vertical distances here from each point to the line, you square those, add them up. This is the line that has the smallest among all the infinite possible lines you could put through these data. I find that pretty amazing. Okay, it turns out that beta 0 is 1.06 and B1 is 1.06, B1 is 0.35. The fitted line, therefore, is 1.06 plus 0.35x. What does that mean? It means for each 1 second delay in giving the injection, the seizure duration increases by approximately 0.35 minutes. Notice the units I'm working with here. So the hypothesis of interest is usually, is the slope equal to 0 versus not? In other words, does this variable affect that one at all? And if the slope were 0, it says it doesn't really matter what the latency is. It wouldn't affect seizure duration. Versus, is the slope not equal to 0? The p-value in this case happens to be 0.0019. So we would claim that this slope is significant. There is a significant linear relationship between injection latency and seizure duration. Furthermore, we can get confidence intervals for this slope, and it turns out it's approximately between 0.15 and 0.55. Almost should be approximately, halfway between 0.35 should be right in the middle there. So recall the correlation coefficient for these data was 0.65. There's another little thing we can define called the coefficient of determination, which is called r squared, and that lies between 0 and 1. Now this is about the easiest thing we can do in this lecture, is just square r. If you take 0.65 squared, you get about 0.42, and it turns out that is equal to the proportion of variability in y that is explained by the linear relationship with x. So in other words, 42% of the variability in y, which would mean if I looked at y just along the y-axis, so you can imagine these points, how do they live on the y-axis? 42% of that variability is explained by x. That's pretty darn good. Just as with ANOVA, a regression model can have several x variables, each with its own slope. So again, once you jump the gun to 2, going beyond that, it just gives you more lines. And it's more complicated to work out, but the computer does it, so it's not any real problem for us. So this brings us to this issue. Now, in medical applications, as well as many others, it's often the case that the response variable is dichotomous. There are only two possibilities. It's not a nice continuous thing like seizure duration is basically a continuous variable that lives on the continuum of time. For example, if is the patient seizure-free after 1 year post-surgery? That's just a yes or no answer. So y could equal 0, 1, say, where 0 means no and 1 means yes. Of interest is the probability of being seizure-free 1 year after epilepsy surgery as a function of the age of epilepsy onset. Well, that looks kind of interesting. But if you do a regression here, if I draw a straight line, notice I've only got zeros and ones on the y-axis. Straight line doesn't look very promising. One reason is that a straight line will extend past 0 or 1, and so we will need an appropriate model for data like this. So that brings us to one of the final topics today, which is logistic regression. And logistic regression, as we recall in the last slide, as before, y is still a dependent variable, but now it's binary. It's just 0 or 1. And so the value of interest is not y itself, but the probability that y is equal to 1, say. It's the probability of the event occurring. Now, this could be bad, the disease is present or not. It could be a good outcome, the patient seizure-free 1 year after surgery. That would be a 1, and 0 would be they're not. And so we have something called a logistic model. And here we will look at something called the logit of the probability, which is the logarithm of the odds. P over 1 minus P are the odds. So if you ever hear people talk about odds in sports, it's always the probability of something happening over the probability that it doesn't happen. And it is this that we model as a linear function in X, where X could be, say, age of onset of epilepsy. So here, P over 1 minus P is the odds of an event occurring, and we now have a linear regression model, similar to what we've seen before, but where the response is the logit. And the logit is the logarithm of the odds. The nice thing is the logit now is not restricted to lie between 0 and 1. The logit, if P is equal to 1, then, or as it gets close to 1, that's 1 over something that's going to 0. That's going to infinity. If P goes to 0, then you've got something, a logarithm of something that's 0. The log of 0 in limit goes to minus infinity. And so we don't have that problem we had with fitting a straight line through these data. And as you can see, a little bit of algebra, very little, shows that the probability of y equaling 1 is equal to this value, which again forces P to lie between 0 and 1. It's P that has to lie between 0 and 1, not the logit anymore. So let's take a look and see what happens. So as with linear regression, logistic regression fitted models provide estimated parameters. From the data before with the SysCom data, we get an estimated logit, and we just did a linear regression there. A little bit more involved than that, but basically we got our 2 parameters. Okay, so we do need to note here that the dependent variable is y still, which is 0 or 1, but the logit is what is estimated. So we estimate the log of the odds as minus 1.81 plus 0.32 times the age of onset. So that's the log of the odds of being seizure-free after 1 year. It's a mouthful. The p-values for the intercept are 0.014, and the slope is less than 10 to the minus 4. Well, that's all well and good. What does it mean? You're all saying. I don't blame you. What's the effect of being 1 year older for age of epilepsy onset? Well, if we go strictly by our line, in this case, slope and intercept, it says, oh, it increases the logit by 0.32. Well, what does that mean? Well, it turns out increasing the logit by 0.32, remember the logit is in log scale, so if we take the anti-logarithm or exponentiate it, we get that an increase of 1 year increases the odds by a factor of 1.38. So it increases the odds of seizure freedom by about 38%. And as you all know, at least I am told by my expert colleagues that the later the age onset, the better the outcome can be. So further, the 95% confidence interval for this odds ratio is 1.21 to 1.56, almost halfway in between. It's not quite like it was in linear regression, or an increase between 21 and 56%. So that is odds ratio, which is something you're going to see a lot of when you do logistic regression. And we do a lot of these here. And so that's logistic regression. Let's take a look and see what it really looks like. And this is really the proof of the pudding. I mean, you can see, at least for the data as I simulated it, as age onset increases, you do tend to see more success up here and less success down here. But notice we're never going to break. We're never going to break through that cap of 1 or the floor of 0. So logistic fitted models will always lie between 0 and 1, but they're going to curve. And that's why we go through all that trouble with the exponentials. It will, even as age onset goes off to infinity, say, it's still going to be bounded by 1 and below by 0. Okay, we're almost near the end, so let's look at extensions to these topics. Analysis of covariance is something that you will run into, at least the term, henceforth ANCOVA. Recall in the analysis of variance, the response is a function of a group category, and regression is a response or linear function of a continuous variable. Can we combine the two, you're asking? And of course we can, otherwise I wouldn't bring it up. Model the jth response from the ith group as before. So we have now Yij is equal to some overall mean, say, or some overall level, plus the effect of being in the ith treatment group, plus a regression term for this covariate x. So x represents the continuous covariate, and beta is its slope. And epsilon ij, as usual, is the noise that we will try to control. And this is analysis of covariance, or ANCOVA. In this model, if there are k treatment effects and the tau i's are not all equal, then the different levels of treatment will be represented by parallel lines in the xy plane, because the tau i's go along with intercepts. The slope's not changing. The common slope beta is going to be the same, but the intercepts will be all of these fellows, alpha plus tau i's. But what if beta is 0? You know, we've already seen from regression that the slope could be 0. Then the ANCOVA reduces to a one-way analysis of variance. And so you're probably asking, can we test for different slopes? Well, sure we can. Otherwise, I wouldn't have brought it up. So we have Yij now could equal alpha plus tau I, the effect of being in the I treatment group, plus some overall slope based on the covariate x, plus individual slopes for each treatment group. And here gamma I represents the interaction between the ith treatment and the covariate x. We can test for this interaction term, say the gamma i's are all equal, in other words, it doesn't matter, to at least one pair being not equal. And if this is significant, then the slope for the ith treatment group is beta plus gamma I. If not, in other words, if there is no treatment-specific slope for this covariance, then we're back to our previous analysis of covariance, and we go along from there. Last but not least is multivariate analysis of variance, or MANOVA. And we'll go briefly over this, because these can be pretty complicated models, but what if the response has more than one value? For example, your response is seizure frequency and seizure severity. So instead of a single Y as a response, in general, you can have a whole host of points, not just two. We might as well go all the way to n as the response variable. And so in this case, we have a multivariate analysis of variance. The multivariate means that the responses are multi as opposed to the x's. We can test for the overall effect of x, say, on these responses, and that's a multivariate f-test. If this is significant, then we may want to test for the significance of x on the individual y's, or the y1 through yn separately. In other words, if the multivariate test is significant, then the univariate tests are conducted. This is similar, if you think about it, to the overall p-value being significant and an ANOVA being necessary to conduct post-hoc tests. So you may see MANOVA. It's usually, in my experience, very often in social science settings. You may hear terms like repeated measures come up, but we don't really look at them as in a MANOVA setting anymore. So in summary, to summarize, all models discussed here are examples of linear models. When the response is continuous, least squares is the method that is used most often, but other methods exist. And Some of you, the more mathematically inclined, might have been thinking all along, well, why do we care about squared distances so much? Why not look at the absolute value? Why bother squaring? I mean, absolute value is a good distance measure, right? And you would be right. That's called least absolute value regression. Sometimes we call it least abs. And that's a possibility too. Turns out it's actually a little more complicated than least squares, but that's for mathematical reasons. But there are lots more other ways of doing regression than least squares. When the response is dichotomous or polychotomous, then logistic regression is used more often. It doesn't have to be bivariate. It could be multi-categorical. But again, other methods exist. For example, in clinical chemistry, a lot of probit models are used, where instead of a log of the odds ratio, the inverse of the normal distribution is used to create a nice S-like curve. Remember, the logistic curve went from the lower left to the upper right in our case. It could go the opposite direction, but it had a nice bend to it which kept it between 0 and 1. There are other functions which do that. The inverse of the bell curve distribution is used to do that. So just to let you know that there are more complex things and to discuss them with your local statistician for clarification. Well, I hope this was useful and you got a lot out of it.